Hello viewers, welcome to this module on miscellaneous topics in classical linear regression model. In this topic, we will deal with three main things. First, we will take a look at regression through the origin. After that, we will look at regression using standardized variables, and finally, we will take a look at prediction in the classical linear regression model. So, we begin with the first subtopic of this module, that is regression through the origin. Up until now, what we have done is we have included an intercept term in the regression. So, now for the first time we are omitting the intercept and we begin with the following model. So, you can see that y is being regressed on x2, x3 through xk, and there is a random disturbance term ui, which follows all the classical properties, all the assumptions of the classical linear model. The only thing that is absent from the model is the first intercept, that is beta 1. So, this model again, because it follows the classical properties, is estimated by using the ordinary least squares method of estimation. And when we minimize the error sum of squares, we obtain the normal equations. So, the normal equations now are given as summation y I x to I is equal to beta 2 summation x 2 I squared plus beta 3 summation x 3 I x 2 I plus beta k summation x k I x 2 I, and of course, these are to be estimated. So, we put beta 2 hat, beta 3 hat up to beta k hat. Similarly, the same thing happens for the variable x3, and this goes through up to y I x k I, that will again be equal to beta 2 hat summation x 2 I x k I plus beta 3 hat summation x 3 I x k I, and right up to beta hat k summation x k I squared. So, we have these normal equations which are solved to obtain the estimates, beta 2 hat right up to beta k hat. Now, you would have noticed that the first normal equation begins with the product of y I x 2 I. So, therefore, unlike the earlier model where we had an intercept, the basic difference here is that here summation E I is no longer equal to 0, I going from 1 to n. The others are still valid, that means summation E I x 2 I is equal to 0 right up to summation E I x k I is equal to 0. So, therefore, in this model we cannot say that y bar is equal to y hat bar. This property no longer holds. Accordingly, for this model, the next step is also a little bit affected in the sense that when we decompose the sum of squares, we have to now use y is equal to y hat plus e, but we cannot write y bar is equal to y hat bar. Earlier we had been able to write y bar is equal to y hat bar plus E bar because this was equal to 0. Now, this condition is no longer valid. So, we have to go by the method of decomposition where we say y I is equal to y hat I plus E I. So, therefore, the total sum of squares is now defined as summation y I squared I running from 1 to n, where this capital Y I is different from the earlier small y I. Earlier we had used small y I is equal to capital Y I minus y bar. Now, this is replaced by capital Y I squared. So, total sum of squares is summation y I square. Explained sum of squares is now given as summation y hat I squared, I going from 1 to n, where y hat is this y hat which we obtain when we replace the parameters with their estimates and omit the random disturbance term, and residual sum of squares is given as summation E I squared, I running from 1 to n. In matrix notation, what we write is y prime y is equal to y hat prime y hat plus E prime E. So, two things. First, the original format gave us a normal equation which allowed us to write summation E I is equal to 0, which is no longer true, which means that we cannot make any mean correction. So, small y is not the variable that we are using the variable capital Y I. Total sum of squares, explained sum of squares and residual sum of squares are all not corrected for mean. These are before the mean correction, or these are without the mean correction. So, that is the basic difference. Accordingly, we can now write the sampling distribution of beta hat as follows. So, beta hat in the first place is now given by beta 2 hat, beta 3 hat up to beta k hat, because beta 1 is absent from the model, beta 1 itself is absent from the model. So, that is given as x prime x inverse x prime y, where x, the matrix X earlier was x1, x2 right up to xk, but now the first column is no longer there. So, earlier we had n observations, n rows and k columns, but now we have n rows and k minus 1 columns. So, x prime x therefore is of order, it is of order not k cross k, but k minus 1 cross k minus 1, and beta hat is therefore following a normal distribution with mean beta and sigma square x prime x inverse. The notation is as earlier, only thing is this x prime x matrix has order, it is a square matrix of order k minus 1 cross k minus 1, and this beta has k minus 1 rows and 1 column. This has k minus 1 rows and 1 column. That is because we have 2 from 2 to k. Accordingly, we can now use this, and the estimate of sigma square hat, earlier it was RSS divided by n minus k, because we had k elements here beta 1 through beta k regressors. Now, we have k minus 1. So, sigma square hat is estimated by RSS divided by n minus k minus 1, and RSS, as we have already seen, is defined as E prime E, where E is y minus y hat. So, using these two pieces of information, that is the sampling distribution of beta hat and the estimate of sigma square hat, we can carry out all the tests that we had carried out earlier in the original model where there was an intercept term. So, these are the main features, the main points of departure for the regression through the origin as compared to the regression where we have an intercept. Having done that, the next thing that we take up now is regression using standardized variables. So, first we define a standardized variable. So, supposing we have, just for simplicity of exposition, supposing we have the model y I equal to beta 1 plus beta 2 x 2 I plus u I, where u I follows all the classical properties. Now, we define y I star as y I minus y bar divided by standard deviation of y. So, that is the standardized variable, the variable minus its mean divided by its standard deviation. Similarly, we define x I star as x I minus x bar divided by standard deviation of x. And as you will have noted, the first variable is just the unit vector. So, when you standardize the model, this unit vector minus its mean gets eliminated. So, in terms of y star and x star, the model is rewritten as y I star is equal to beta 2 star x 2 I star plus u I star. So, this now is the model where we are running a regression of standardized y on standardized x, and this becomes immediately relevant because just a few minutes back we had taken a look at a model where we had a regression through the origin. So, the original model has been transformed into a regression which is running through the origin. Similarly, if we had x3, x4 and so on, we could have standardized all the variables and we could have obtained y I star regressed on x2 I star, x3 I star through xk I star. Now, why do we do this? We do this because when we write a standard regression model, then y I is equal to beta 1 plus beta 2 x 2 I plus dot 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 beta k x k I plus u I, where these variables are measured in different units. This may be GDP, this may be something else. So, these are different units, and even if these are statistically significant, that means even if this is the estimated model, so that we have y I hat equal to beta 1 hat, beta 2 hat up to beta k hat. So, if this is given in millions of rupees, x 2 I is given in millions of rupees, y I is given in millions of rupees, whereas beta k I may not be given in million rupees, may be given in some other physical units. So, these coefficients are also interpreted in terms of the units of measurement of these variables. Accordingly, we cannot compare directly beta 2 hat and beta k hat. So, beta 2 hat is the sensitivity of y I per unit of change of x 2 I, beta k is the sensitivity of y I per unit of change of x k I, but x k I and x 2 I are measured in different units. So, it is difficult to compare these two, but once they are in standardized units, y I star and this gets eliminated, x 2 I star and x k I star. So, now we can say that each variable is measured in standardized units. So, we can compare the coefficients or the regression coefficients when the regression is done in terms of standardized variables directly. That is the benefit of running a regression using standardized variables. Before we go to the next part, what we would like to show is what is the relation between the estimated coefficients in original variables vis-a-vis the coefficients in standardized variables. So, let us take a look. When we are regressing y I star on x 2 I star, applying the ordinary least squares formula, what we have is beta 2 hat is equal to summation y I star times x 2 I star divided by summation x 2 I star squared. This is the same formula that we have been using right from the 2 variable model up to the k variable model with suitable modifications. Only thing is, now we are using, as you have noted, instead of small lower case letters, that is instead of mean corrected variables, we are using original variables. So, let us now substitute y I star. Y I star is y I minus y bar divided by s of y, standard deviation of y, and x I star is x I minus x bar divided by standard deviation of x. So, y I star times x 2 I is x 2 I star is x 2 I minus x 2 bar divided by standard deviation of x 2, and we sum this up and we divide by x 2 I minus x 2 bar divided by standard deviation of x 2 and whole square. And here you will notice that in the numerator you have one element sy, another element sx2, and in the denominator you have sx2 whole square. So, this flips up and you have beta 2 star hat. This is the regression with standardized variables. So, this will be beta 2 star. So, beta 2 star hat will be beta 2 times, since this goes up, you have sx2 square divided by sy times sx, and so one of these gets cancelled. So, you have this beta 2, which is our original one, yi minus y bar, and we have this as beta 2 sx2 divided by sy. Now, let us take a look at prediction in the k variable classical linear regression model. So, the model, as we already know, is yi is equal to beta 1 plus beta 2 x 2 I plus right up to beta k x k I plus u I. And once the model is estimated, we have y hat I, beta 1 hat, beta 2 hat up to beta k hat, and the random disturbance term is not there. Now, supposing we are given x f represents an unknown time period or an unknown observation, to be more accurate, that is equal to 1 x 2 f x 3 f right up to x k f. So, it is the fth observation which comprises 1 corresponding to the intercept, 2, 3 right up to k. We want to predict yf, we want to predict yf. So, from the estimated model, in the estimated model we fit this observation, the fth observation, and we want to predict this. Naturally, since we already have by the Gauss-Markov theorem, the basic result is from the Gauss-Markov theorem, we know that the basic result is if we have a row vector C prime, then C prime beta hat is the best linear unbiased estimate of C prime beta. So, we apply our OLS estimate and what we write is estimate F corresponds to the estimated beta vector evaluated at the fth observation. So, that is our prediction of the y value at the fth observation. Now, two cases are possible. First one is we want to predict the expected value of yf. We want to predict this. So, the expected value of yf is beta 1 plus beta 2 x 2f plus beta k x k f plus expectation of uf. Students, you will notice that the true yf would be beta 1, beta 2, x 2, beta k x k plus uf, and the expectation of this is equal to 0 by the classical property. So, expected value of yf is just the beta terms times their corresponding x values. And how do we estimate this? So, we want to estimate this, we estimate this with the help of y hat f. So, this gives us a very interesting result, that is y hat f minus expectation of y hat yf divided by sigma times root over x f prime x prime x inverse x prime x f. This follows a t distribution with n minus k degrees of freedom. This is the same result that we would have obtained if we had tried to form a distribution of any of the beta hats. So, this is estimate minus expectation of that divided by, as you know, this is sigma hat RSS by n minus k and the square root of that, and this is nothing but the variance covariance. So, you have a row vector x f prime and that you multiply with x prime x inverse post multiply with x f. This comes from the fact that variance of u is equal to sigma square x prime x inverse variance of u. So, variance of any x f prime times this will be x f prime sigma square x prime x inverse and again x f, and this sigma square is estimated as sigma square hat, and when we take the t distribution we have to have the standard deviation. So, this is a scalar because you have a row vector in front, and so that is the result that we use to form the t distribution. So, that this gives us the confidence interval, the confidence with which we can make the prediction. What is that confidence interval? The confidence interval for expected value of yf, that is given by y hat f plus and minus t at the a% level or a by 2 n minus k times, this is the standard error. So, standard error. So, that gives us, this denominator is the standard error. So, that is the confidence with which we can predict the expected value of yf. One small thing before we end this module, if instead of expected value of yf, we are interested in predicting yf, if we want yf, then the formula gets modified and we write y hat f minus yf divided by sigma hat as earlier, and we have here 1 plus x f prime x inverse x f. So, that now follows a t distribution with n minus k degrees of freedom. The reason this happens is when you want yf, then that uf term does not vanish. Earlier we had concentrated on expectation of yf. So, expectation of uf had become equal to 0. Now that we do not want expectation of yf, we want yf to be predicted. So, this is no longer equal to 0. This has a variance sigma square, and that is being estimated by sigma square hat. So, here again from this we can find the confidence interval for yf. What is the confidence interval? We say it is y hat f plus and minus t a by 2, that is the level of significance. 1 minus a into 100 is the level of significance, and n minus k times this is now the standard error. So, we write this as the standard error. So, that is the confidence with which we can predict yf. So, my dear students, we now come to an end of this module. Do go through the detailed academic script and please update yourselves, work out the exercises, work out the result, work out the derivations given in the PowerPoint and the academic script, and looking forward to meeting you in the next module. Thank you.